Hi, our team is planning to use time series to forecast natural gas consumptions, and this is our agenda. So natural gas is an important energy source and is gaining its popularity recently. It's a clean energy because it only produces like 30 to 50% or less carbon dioxide than burning coals or oils. And natural gas is produced underneath the Earth's surface and can be stored as either liquid or gas state. And we use it to like make materials or heatings or chemicals. And the price of natural gas can be pretty volatile during the year because of the supply and demand issues. The United States has abundant natural gas supply, but during winters or summers, the demand of natural gas usually have a spike, and that causes a temporary supply shortage. So uh, for this project, we are trying to predict the natural gas consumption. So for business like storage company and consumers, they can use it to better forecast that supply shortage. The data we use comes from EIA and has the time range from 2001 to 2020. Uh, the data is the data has the monthly consumptions and has a total number of 240 observation points. And we use 80% of the data for training purposes and 20% for testing purposes.
Okay, so at first we decided to conduct four simple forecasting methods, including average, naive, seasonal naive, and drift methods. So looking at the plot, we can see that the seasonal naive method performs the best among others, since it captures well on the seasonality of our data. Then we check the accuracy of all four methods, and then the result also proves that the seasonality has the lowest RMSE. However, although the seasonal naive performs better than others, it cannot accurately forecast the peak and the lowest point of our data. So by using the jump box test, we can see that the p-value is really small, which indicates that the residuals are not white noise. Therefore, we decide to use the simple forecasting models as benchmarks to evaluate others. And next, we're getting into the exponential smoothing method. Since there's no obvious trend in our data, so we decided to skip the simple exponential smoothing and hot linear method. So we decided to use the seasonality forecast method from the hot winters family, which are additive and multiplicative. And we tuned our methods to be either damped or not. So from the plot, we can see that all forecasts results are quite similar. So we move forward to check the jump box test results. And all the p-values are approximately equals to 0, which suggests that residuals have autocorrelations. Therefore, we compare the accuracy of all methods, and the hot winters additive method has the lowest RMSE and MAPE. Besides, both damped methods are having low accuracy, which indicates that damping has less effect on our data because long-term data don't vary from short-term data. So we can conclude that the hot winters is not an efficient method for our forecast.
Besides hot winter method, ETS model also handles seasonality. It consists of an error term, a trend component, and a seasonality component. So this is our graph for it. Our final pick is the MAA model. Here is a forecast and the residuals ACF plot. I'll go over our selection process now. In our first attempt, we used the ETS function in R, which gave us the best fit model, the lowest AICCs. The model is multiplicative error, no trend, and multiplicative seasonality. However, we don't believe the lowest AICCs model will guarantee the best accuracy at the end. So in the next steps, we tried different combinations of error, trend, and seasonality. All of our 6 combinations have similar scores, ranging from 5400 to 5450. So we move forward to check if residuals are white noises using ACF plot, Junebox text, and t-test mean. Lastly, we compare the accuracies on test data and concluded that the MAA combination is our model of choice. You can see the residuals are representing white noise with just 2 outside borders. Here shows a comparison between the best fitting model and the highest accuracy model. The later one achieved 5.2% MAPE. We also see that the blue line is coming closer to the black line actual data compared to the forecast from the MNM model from the lowest AICCs.
Next, we try the seasonal ARIMA model. Because we use the functions to forecast the number of different things, we need to make our training data set stationary in advance. So we know it is necessary to make one regular differencing and one seasonal differencing. However, we don't know the specific values we should set for upper and the lowercase p and q. So we use the auto ARIMA function without stepwise. Well, first, both regular differencing and the seasonal differencing be equal to 1. Based on the result model from auto ARIMA function, we made some variation on lowercase p and q to check if there are any other models can generate better forecasts. Since accuracy is the golden standard to select the final model, we picked the seasonal ARIMA model with slightly higher AICC, white noise residues, but the highest accuracy. After we try out models and methods we learned in the class, we are curious about how other advanced models perform on our data. So we tried additional 4 models. The first additional model is time series linear model. Since they are both seasonality and the trend in our training data, we use the both trend and the season as independent variables to analyze total consumption of natural gas. However, the p-value of Junebox test is extremely small, and the most lags in AIC plot is lying outside the 95% confidence interval, which indicates the model is inefficient to catch some information left over in the residues. Therefore, the accuracy of the time series linear model is just moderate.
Our second additional model is the T-BETS model. T-BETS model is capable of modeling time series with multiple seasonalities, such as weekly and yearly seasonal patterns. T stands for trigonometric, B for Box-Cox transformation, A for ARMA error, T for trend, and S is for seasonalities. Interpreting this model, we can see that the model has a Box-Cox transformation of 0.534. Error is modeled as an ARMA21 process. 12 seasonal period is used in the model and 5 corresponding Fourier terms used for each seasonality. This model has an AICC of 5,407, and the residual shows the p-value of 0.2443, meaning that it follows a white noise pattern. And the RMSE for our T-BETS model is 258,000, a relatively moderate value. Our third additional model is the NNAR model, which is neural network autoregressive model. Just as we can use lag values in linear autoregressive models, lag values of time series can also be used as inputs to a neural network. The neural network autoregressive one is one kind of artificial neural network in which lag values of the time series can be used as inputs to a neural network. Interpreting this model, we can see that the model is a seasonal one with parameter 1418, which is similar to an ARIMA model as shown above, but with nonlinear functions. The p-value for this model's residual is 0.314, meaning that it follows a white noise pattern, and the RMSE for this model is 274,000.
Now we have gone through all methods and models. In our last step, we evaluate all our models against seasonal naive from benchmark category. First model needs to pass white noise test of residuals. So you'll see from this table here, EDS, seasonal ARIMA, TBET, and NNAR passed the white noise check. Here is a plot of forecast from all these 4 models against the test set data. Graphically, we can hardly observe the best one. So from a statistical approach, we compare the accuracy of them on a test set. The RMIC of seasonal ARIMA is the lowest one. So this becomes our final model of choice.
So finally, we use the ARIMA model to predict the next 3 months of natural gas consumptions, and we can see that it has an overall upward trend with a strong seasonal patterns. And from that, we can give some advice to 3 kind of business. First, because of the supply shortage at those peaks, those storage companies should closely monitor the weather conditions and to increase their inventories accordingly to avoid it. And because the shortage could cause the spike in price, power companies should consider to use swaps to protect them from those volatile prices. And also, with increasing demand, natural gas miners should continue to develop more advanced and cost-efficient technology to increase their production. And that's the end of our presentations. Thank you.